Picture this. You're floating in the darkest ocean you've ever seen. But this isn't water. There's no up, no down, no light, no sound. And you're not just lost. You're in a place where the very fabric of reality begins to tear apart. Welcome to the universe's most terrifying destinations. Today, we're going to take you on a journey to 12 places in our cosmos that will make you question everything you thought you knew about existence. Places where time breaks, where space tears, where matter itself screams as it's ripped atom from atom. But here's what really keeps astronomers up at night. Every single one of these places is real. They're out there right now, and some of them are coming for us. If you like the content, leave a like and subscribe to the channel, because by the end of this video, you'll never look at the night sky the same way again. Because what we're about to show you isn't science fiction, it's science fact, and it's absolutely terrifying. Let us start. Chapter 1. The Great Nothing. Let's start with something that shouldn't exist. A place so empty, so impossibly void of everything that scientists didn't believe it was real when they first discovered it. It's called the Boortes Void. But astronomers have another name for it. They call it the Great Nothing. Now you might be thinking, space is already empty, right? What's so scary about more emptiness? But you don't understand. The Great Nothing isn't just empty, it's wrong. Here's what I mean. On average, every cubic megaparsec of space contains about 10,000 galaxies. 10,000 entire galaxies, each with billions of stars. That's normal. That's what the universe looks like almost everywhere we point our telescopes. The Great Nothing has 60. Let me say that again. In a region of space 330 million light-years in diameter, where there should be millions of galaxies, there are only 60. It's a sphere of cosmic emptiness so vast that if our Milky Way galaxy was sitting in its center, we wouldn't see another galaxy in any direction for hundreds of millions of light-years. We'd be alone, completely, utterly alone in the dark. But here's where it gets disturbing. We don't know why it's empty. In 1981, astronomer Robert Kirshner was conducting a survey of galaxy redshifts. Routine work. Boring even. He was mapping the cosmic web, the vast structure of galaxies that fills our universe like a three-dimensional spider's web stretching across billions of light-years. Then he found the hole. At first he thought it was an error, a glitch in the data, because what he was seeing was impossible. As he mapped more and more of this region, the emptiness just kept growing and growing and growing. His colleagues didn't believe him. They couldn't believe him, because the existence of something this empty violated our understanding of how the universe formed. After the Big Bang, matter should have spread relatively evenly throughout the cosmos. Sure, there are denser regions where galaxies form and less dense regions between them. But the Great Nothing isn't just less dense, it's almost completely empty, like someone took a cosmic vacuum cleaner and sucked almost everything out. So what happened there? Theory 1 is the most disturbing. Some scientists believe the Great Nothing could be evidence of a bubble universe. Stay with me here. According to certain interpretations of quantum mechanics, our universe might not be alone. There could be other universes, other realities, pressing up against ours like bubbles in foam. If another universe collided with ours billions of years ago, it might have created a shockwave that pushed all the matter aside, leaving behind this empty bubble. The Great Nothing could be a scar from a cosmic collision we can barely comprehend. But theory 2 might be even worse. It's possible the Great Nothing is still growing. You see, there's something else strange about this void. The few galaxies that do exist inside it seem to be moving. being pushed by something. Some force we can't see is actively clearing out this region of space, making it even more empty over billions of years. What force? We don't know. We can't see it, can't detect it. We only know it's there because of what it's doing to the galaxies. Imagine standing in a dark room and feeling a wind on your face, but when you look, there's nothing there. That's what the Great Nothing is like for astronomers. They can see its effects, but they can't see what's causing them. And here's the truly terrifying part. The Great Nothing isn't alone. Since its discovery, we've found more voids, lots more. The universe is full of these cosmic empty spaces, like holes in Swiss cheese. There's the giant void, the Capricornus supervoid, the CMB cold spot, which might be connected to an even larger void we haven't fully mapped yet. Our universe isn't the smooth, evenly distributed place we thought it was. It's full of holes, vast, inexplicable absences of everything. But what really keeps cosmologists up at night is this question. What if these voids are growing? What if, billions of years from now, they merge and consume more and more galaxies until there's nothing left but darkness? The universe could be slowly emptying itself out, and we're watching it happen in real time, powerless to stop it or even fully understand it. Now, imagine being an intelligent civilization that evolved inside the Great Nothing. You'd develop science, build telescopes, study your world, and when you finally looked up at the night sky with technology powerful enough to see distant galaxies, you'd see nothing, just darkness, forever. You'd conclude you were alone, that your galaxy was the only one in existence. The entire universe, as far as you could tell, would be just you and endless emptiness. You wouldn't even know to search for other life because you'd have no evidence that other galaxies existed. That isolation, that cosmic loneliness. That's one kind of terror the universe offers. But we're just getting started. Because while the Great Nothing is disturbing in its emptiness, our next destination makes it look like child's play. Chapter 2. The Eridanus Supervoid. In 2004, astronomers discovered something that shouldn't exist. Something so vast, so cold, so empty that it breaks our most fundamental theories about how the universe works. They were studying the cosmic microwave background, the CMB. Think of it as the echo of the Big Bang, radiation that's been traveling through space for 13.8 billion years. It should be perfectly uniform, showing the same temperature in every direction we look, give or take a few millionths of a degree. But it's not. There's a cold spot, a massive region of space where the temperature is significantly lower than it should be. And when scientists looked at what was causing it, they found the Eridanus supervoid. This isn't just another empty region. The Eridanus supervoid is a space 1 billion light-years across with almost nothing in it. To give you perspective, that's about 3 billion trillion miles of nearly empty space. If you travelled at the speed of light, it would take you 1 billion years to cross it. Nothing should be able to create an empty space that large. Our models of cosmic structure formation simply don't allow for it. And yet, there it is, staring back at us from the constellation Eridanus. But the emptiness isn't what scares scientists, it's what the emptiness means. You see, according to our understanding of physics, the Eridanus supervoid should be filling in. Dark matter and dark energy should be drawing galaxies toward it, gradually filling the space over billions of years. But that's not happening. Instead, it seems to be repelling them, pushing galaxies away. Think about that. There's a region of space 1 billion light-years across that appears to be actively rejecting matter, like reality itself doesn't want anything there. Some cosmologists have proposed a disturbing explanation. What if the Eridanus supervoid isn't empty because matter never formed there? What if it's empty because something is making it empty? One theory suggests we might be looking at evidence of dark energy behaving in ways we don't understand. In most of the universe, dark energy is driving cosmic expansion at a relatively steady rate. But in the Eridanus supervoid, it might be accelerating, creating a bubble of space that's expanding faster than the surrounding universe, pushing everything out. If that's true, then the Eridanus supervoid is like a cancer in the fabric of space-time, growing, consuming, expanding. And here's what really disturbs physicists. It might not be the only one. Remember that CMB cold spot I mentioned? It's so large and so cold that some scientists have suggested it might be evidence of something even more terrifying than a supervoid. It might be a bruise on our universe, left by a collision with another universe. Let that sink in. We might be looking at proof that something from outside our reality touched us. And where it touched us, it left a wound. But there's another theory about the Eridanus supervoid that's even more unsettling. Some physicists have suggested it might be a region where the fundamental constants of nature are different. The speed of light, the strength of gravity, the charge of an electron. These constants define reality as we know it. They make chemistry possible, allow stars to form, let planets exist. If they were even slightly different, atoms couldn't form. Stars wouldn't shine, life couldn't exist. What if inside the Eridanus supervoid, these constants are different? Not by much, just enough to make it inhospitable to matter as we know it. Just enough to create a bubble of alien physics where normal matter simply can't exist. If that's true, then the Eridanus supervoid isn't just empty. It's a region where the rules of reality are different, where the universe is fundamentally alien. Now imagine what would happen if you could somehow travel there. As you cross the boundary, the laws of physics governing your body would begin to change. Atoms would interact differently. Chemical bonds would weaken. Your DNA would unravel. You wouldn't explode or freeze. You'd simply stop being able to exist. Your matter would reject the space itself, just as the space rejects matter. That's a special kind of cosmic horror, not a monster coming to get you, but a place where you simply couldn't be, where your very existence is incompatible with reality. But here's the question that haunts cosmologists. If the Eridanus supervoid is a region of altered physics, what created it? What could fundamentally change the rules of reality across 1 billion light-years of space? Some theorists have proposed that during the first moments after the Big Bang, quantum fluctuations could have created bubble universes within our universe. Regions where inflation ended differently, creating pockets with slightly different physical constants. If that's what the Eridanus supervoid is, then it's not alone. There could be thousands, millions of these bubble universes within our own universe. Islands of alien physics. Places where reality is fundamentally wrong, and we might be completely surrounded by them, never knowing they're there unless they happen to be empty enough for us to notice. That's the terror of the Eridanus supervoid. It's not what it is, it's what it represents. Evidence that the universe we think we understand might be just one island of familiar physics in an ocean of incomprehensible alien realities. But at least the Great Nothing and Eridanus supervoid are just empty. They can't hurt us from trillions of miles away. Our next destination is different because it's pulling us, right now, this very second. Something massive, something incomprehensibly powerful, is dragging our galaxy and millions of others toward it at over 1 million miles per hour, and we have absolutely no idea what it is. Chapter 3: The Great Attractor. In the 1970s, astronomers noticed something disturbing. Our galaxy was moving wrong. The Milky Way is travelling through space at about 370 miles per second. That's normal. Galaxies move. What wasn't normal was the direction. We weren't just moving with the expansion of the universe. We were being pulled towards something massive, something hidden. They called it the Great Attractor. And here's what makes it absolutely terrifying. We still can't see it. Imagine you're swimming in the ocean and you feel a current, a strong current pulling you in one direction. You look to see what's causing it, but there's nothing there, just water. But the current is real, it's pulling you, and it's getting stronger. That's what the Great Attractor is like. We can measure its effects on hundreds of thousands of galaxies across hundreds of millions of light years, but we can't see what's causing it. Why not? Because it's hidden behind the zone of avoidance. The zone of avoidance sounds like something from a horror movie, and in a way, it is. It's the region of space hidden behind the disk of our own galaxy. The Milky Way's dust and stars block our view, creating a blind spot in our observations. A cosmic curtain we can't see through, and the Great Attractor is hiding right behind it. From what we can observe indirectly, we know it's massive, impossibly massive. It has the gravitational pull of tens of thousands of galaxies, and it's pulling everything toward it. Our galaxy, Andromeda, the entire Virgo supercluster, hundreds of millions of stars, all being dragged inexorably towards something we can't see. We're falling toward it at 600 kilometers per second. That's over 1 million miles per hour, and we've been falling for billions of years. In 1987, a group of astronomers called the Seven Samurai published a study that shocked the scientific community. They'd mapped the motion of galaxies across a massive region of space and discovered that the flow was even larger than anyone thought. The Great Attractor wasn't just pulling nearby galaxies, its influence extended across 650 million light-years. Hundreds of thousands of galaxies, all caught in the same cosmic current, all flowing toward the same point. But here's where it gets genuinely disturbing. In the 1990s, astronomers finally got powerful enough instruments to peek through the zone of avoidance. They expected to find something spectacular, a massive cluster of galaxies, a supervoid causing gravitational focusing, something to explain the immense gravitational pull. What they found was not enough. Yes, there's a large cluster of galaxies there called the Norma cluster, but it's nowhere near massive enough to be the Great Attractor, not even close. It was like expecting to find a mountain and finding a small hill. So where was the rest of the mass? Where was the source of this incomprehensible gravitational pull? That's when astronomers realized something chilling. The Great Attractor wasn't the real attractor. It was just another victim. There was something beyond it, something even larger, even more massive, pulling not just our local cluster of galaxies, but the Great Attractor itself. They called this larger structure the Shapley supercluster. It contains thousands of galaxies and is one of the most massive structures in the observable universe. But even the Shapley supercluster can't fully explain the motion, because as astronomers mapped more and more of the cosmic flow, they realized the pull extends even further, into regions of space we've barely begun to map. We're part of what astronomers now call the Laniakea supercluster. It's a gravitational basin containing 100,000 galaxies, all flowing like water down a drain toward a common center. Our entire supercluster is a river of galaxies flowing towards something. But here's the existential horror of the Great Attractor. We can't stop. We can't change course. We can't escape. Our entire galaxy, our solar system, Earth, you, me, everyone and everything we've ever known, is caught in a gravitational current so powerful that nothing can resist it. We're being carried along like leaves in a cosmic river, heading toward a destination we can't see, can't understand, and can't avoid. And it's been this way for billions of years, long before Earth formed. long before the first stars ignited. The matter that would eventually become us was already caught in this flow, already being pulled inexorably toward the Great Attractor. Now don't panic, we're not going to reach it anytime soon. At our current speed, it would take billions of years. The sun will die long before we get there. Humanity will likely be gone, evolved into something unrecognizable or extinct. But that doesn't make it less terrifying, because it means we're not in control. We like to think of Earth as our home, the solar system as our neighborhood, the galaxy as our realm. But we're not stationary. We're passengers on a cosmic vehicle we can't steer, heading toward a destination we didn't choose and can't see. And here's what really disturbs cosmologists. What happens when we get there? When all those galaxies finally reach the center of the gravitational basin, what happens? Do they merge into one supergalaxy? Do they form a structure so massive it collapses into something else entirely? We don't know. We've never seen the endgame of this process. Some scientists have speculated that regions of extreme gravitational convergence could create conditions we've never observed. Massive black hole formation, exotic matter states, regions where space-time itself becomes so distorted that the normal rules break down. The Great Attractor might not just be pulling us toward it, it might be pulling us toward a region of space where physics becomes alien, where reality itself is different. But there's one more disturbing possibility that a few physicists have quietly discussed. What if the Great Attractor is alive? Now, I don't mean alive like you and me. I mean, what if it's a self-organizing system? What if the concentration of mass and energy creates feedback loops that make it grow stronger, pulling in more matter, which makes it pull even harder? It would be like a cosmic predator, not conscious, not intelligent, but purposeful in its own way, growing, feeding, pulling everything toward itself. And we're caught in its web. That's the terror of the Great Attractor. Not what it is, but what it means. We're not in control. We never were. Our galaxy is just flotsam caught in a cosmic current, heading towards something massive and hidden and completely beyond our power to resist. But at least the Great Attractor is far away, hundreds of millions of light years. Whatever happens there won't affect us for eons. Our next destination is different, because there's one sitting right at the center of our galaxy. Right now, just 26,000 light years away, close enough to be a real danger, close enough to be watching us. Chapter 4, Black Hole Event Horizon. Let me ask you a question. What's the most dangerous place you can think of? A war zone? The bottom of the ocean? The surface of the sun? All of those would kill you, sure, but at least you'd understand what was happening. Your death would make sense. A black hole's event horizon is different, because at the event horizon, reality itself breaks down. The rules of physics that govern everything you've ever experienced simply stop working. And the truly terrifying part? We think there are millions of them scattered throughout our galaxy alone. Let's start with what an event horizon actually is. It's not a physical surface. It's not a barrier you could touch. It's a boundary in space-time itself, the point of no return. Once you cross it, escape becomes literally impossible, not difficult, not requiring advanced technology, impossible, as in forbidden by the fundamental laws of physics. Even light can't escape. And light is the fastest thing in the universe. Nothing can go faster. Which means that once you cross the event horizon, there is nowhere in the entire universe you could go to escape. No direction you could travel. No engine powerful enough to save you. You would be trapped in a region of space-time that's sealed off from the rest of reality. But here's what makes the event horizon truly horrifying. You might not even know you'd crossed it. If the black hole is large enough, we're talking millions or billions of times the mass of the sun, The event horizon could be so vast and the curvature of space so gentle that you'd cross it without feeling anything. No jolt, no barrier, no warning. One moment, escape would be difficult but possible. The next moment, escape would be impossible. And you might not know which side of that boundary you were on until it was too late. It would be like walking through a doorway, except the moment you step through, the doorway vanishes. The room you came from ceases to exist. The entire universe you knew becomes unreachable, forever. That's not just death, that's erasure from reality. Now let's talk about what happens as you approach the event horizon. And this is where physics becomes genuinely nightmarish. As you get closer, time starts to change. Not for you from your perspective, everything seems normal. But to anyone watching from a safe distance, you start to slow down. Your movements become sluggish, like you're moving through molasses. As you get closer still, you slow down more, and more, and more. From the outside, you would never actually reach the event horizon. You just get slower and slower and slower, asymptotically approaching it, but never quite arriving. To the outside universe, you'd be frozen at the edge of the black hole forever. Your last moment stretched out into eternity. But from your perspective, you'd cross the event horizon in finite time. You'd fall through, doomed, while the rest of the universe watched your frozen image hovering at the edge forever. Think about that. There's a sense in which you'd exist in two states simultaneously, frozen at the event horizon forever from one perspective, yet having fallen through and been destroyed from another perspective. Both true, both real, both happening at the same time. That's the kind of reality-breaking weirdness black holes create. But it gets worse, because there's something called spaghettification. As you fall toward a black hole, the gravity pulling on your feet becomes stronger than the gravity pulling on your head. The difference might be small at first, but it grows rapidly. Soon the tidal forces become enormous. Your body would start to stretch, like taffy. Your feet pulled harder than your head, your molecules forced apart, then your atoms, then the atoms themselves torn apart as the distance between your head and feet becomes so great that the gravitational difference overwhelms even atomic bonds. You'd be turned into a stream of subatomic particles, a thin string of matter spiraling down into the black hole, spaghettified. But here's what's truly disturbing. You'd be conscious for some of that. For the first few moments, as your body started to stretch, your brain would still be functioning. Neurons would still fire. You'd feel yourself being pulled apart. You'd understand what was happening, and there would be nothing you could do. No way to stop it. No way to even scream, because the space around you would be so distorted that sound couldn't propagate normally. You'd die knowing exactly what was happening to you, powerless to prevent it. Now there's a small mercy here. For smaller black holes, the tidal forces at the event horizon would be so strong that you'd be spaghettified before you even crossed it. Your death would come quickly, outside the point of no return. But for supermassive black holes, the kind lurking at the centers of galaxies, the event horizon is so large that tidal forces are relatively gentle there. You could cross the event horizon intact, alive, conscious. And that's somehow even more terrifying, because then you'd be inside, past the point of no return, alive and aware, falling toward the singularity, knowing you had only seconds or minutes left before the tidal forces grew strong enough to tear you apart. You'd have time to think, time to contemplate your fate, time to understand that you were now in a region of space-time cut off from the rest of the universe, that no one could help you, that you were going to die and there was nothing anyone could do about it. That psychological horror might be worse than the physical death. But there's one more aspect of the event horizon that keeps physicists up at night. It's called the firewall paradox. According to quantum mechanics, information can't be destroyed. But black holes seem to destroy information by swallowing it. This creates a paradox. And one potential solution is terrifying. Some physicists believe that at the event horizon, there might be a wall of high-energy radiation, a firewall. If you tried to cross the event horizon, you wouldn't spaghettify. You'd burn. Instantly vaporized by a wall of Hawking radiation so intense it would convert your entire body into energy in a fraction of a second. If that's true, then the event horizon isn't an invisible boundary. It's a wall of fire, invisible from far away, but absolutely lethal to touch. And here's the existential horror. We don't know which model is correct. The firewall might exist. It might not. We can't test it without actually going to a black hole. And if we're wrong about which model is correct, we'd only find out at the moment of our death. Imagine approaching a black hole, confident in your understanding of physics, planning to study the event horizon from up close. You cross what you think is a safe boundary and instant incineration. Or not. No way to know until you try. That uncertainty is its own kind of terror. But at least the event horizon is the point of no return. At least once you cross it, the end comes relatively quickly. You fall to the singularity, you're destroyed, it's over. Unless our next destination proves to be something even stranger. Because once you're past the event horizon, you're heading toward a place where all of our physics breaks down completely. Where time and space trade places. Where the universe itself might end. You're heading toward the center of the black hole. And what's waiting there is something we can't even properly describe with mathematics. Chapter 5. The Black Hole Center. At the exact center of every black hole, there's a point where all the mathematics breaks down. Where every equation we use to describe reality produces nonsensical answers. Infinities. Divisions by zero. Undefined values. We call it a singularity. But that's just a fancy word for we have no idea what's actually there. And that might be the most terrifying thing about black holes. Their heart is something that shouldn't exist. Something that can't exist according to the laws of physics as we understand them. And yet it does exist. It must exist, because black holes are real. Let me explain why singularities are so disturbing. When we trace the path of matter falling into a black hole, the equations tell us it gets compressed. The gravity gets stronger and stronger, forcing everything into a smaller and smaller space. This continues until the matter reaches a point of infinite density, zero volume. All the mass compressed into a mathematical point, infinite density, zero volume, infinite curvature of space-time. These aren't just big numbers, they're infinities, and when physics produces infinities, it's usually telling us that our understanding is incomplete, that we're missing something, that reality is doing something our equations can't capture. So what's really at the center of a black hole? We don't know. And the fact that we don't know that our best theories of reality completely fail at this point is deeply unsettling. Some physicists believe the singularity might be prevented by quantum effects, that at incredibly small scales, quantum mechanics might create a repulsive force preventing true infinite compression. The result would be something incredibly dense, but not infinite. Some kind of exotic matter state we've never observed. Others think the singularity might be real, and that physics genuinely breaks down there. That there are places in our universe where the rules simply don't apply, where cause and effect become meaningless, where time and space themselves cease to exist in any recognizable form. That second possibility is existentially horrifying, because it means reality has holes in it, places where existence itself becomes undefined. But there's something even stranger about the black hole's center. Something that violates our intuition about how reality works. Inside the event horizon, space and time trade places. I know that sounds like meaningless science fiction jargon, but it's actually a precise mathematical statement. Here's what it means. Outside a black hole, you can choose where to move in space. You can go left or right, up or down, forward or backward. But you can't choose where to move in time. You're forced to move forward into the future. Always. Inevitably. Inside a black hole, this reverses. You can't choose where to move in space. All paths lead to the singularity. Every direction you try to go, every action you try to take, brings you closer to the center. It's not a matter of going fast enough or having a powerful enough engine. Space itself has become like time. You're forced to move toward the singularity, just like you're forced to move forward in time outside the black hole. But time, inside the event horizon, time becomes like space. You could theoretically move forward or backward in time, though you can't move away from the singularity in space. Let that sink in. Inside a black hole, the singularity isn't a place you're falling toward. It's a moment in time you're moving toward. Your death isn't somewhere ahead of you. It's someone ahead of you. A point in time you're approaching as inevitably as tomorrow comes after today. You can't avoid it by changing direction because direction is meaningless. The singularity is in your future. Period. Just like you can't avoid tomorrow by turning left or right, you can't avoid the singularity by any spatial movement. That's not just terrifying, it's cosmically unfair. Imagine knowing you're going to die at a specific time, and no matter what you do, no matter where you go, that moment will arrive. That's what it's like inside a black hole. But the strangeness goes even deeper. Because some solutions to Einstein's equations suggest that black holes might not end at the singularity. They might continue through to something else. These are called rotating black holes, or Kerr black holes, and the mathematics suggests they might contain a passage to somewhere else. Maybe another part of our universe, maybe another universe entirely, maybe another time. The equations allow for these possibilities, but they also include regions of negative space and closed time-like curves paths through space-time that loop back on themselves. If any of this is real, then the center of a black hole might not be an ending. It might be a doorway. But a doorway to where? To when? And could anything survive the passage? Almost certainly not. The tidal forces and radiation would destroy anything trying to pass through. But the fact that the mathematics even allows for this possibility is deeply weird. It suggests that black holes might be more than just cosmic dead ends. They might be tunnels through space-time itself, connecting distant points in space or time, creating bridges to other universes. Some physicists have speculated that every black hole in our universe might contain an entire other universe. That the Big Bang that created our universe might have been the formation of a black hole in some parent universe. That we're living inside a black hole right now, and every black hole in our universe contains infinite nested universes within universes. If that's true, and I want to stress this is highly speculative, then black holes aren't destroyers of worlds. They're creators of worlds. The singularity isn't an end, it's a beginning. The death of matter in our universe is the birth of matter in a new universe. That's a beautiful idea. It's also terrifying. Because it means that what looks like destruction from our perspective might be creation from another perspective. That every time a star collapses or matter falls into a black hole, entire universes might be born, live, and die in ways we can never observe or understand. We'd be surrounded by an infinite multiverse hidden behind event horizons, forever beyond our reach. But let's return to the more immediate horror of the singularity. Because whether it's a point of infinite density or a doorway to another universe, one thing is certain. If you reach it, you're destroyed. The tidal forces at the singularity would be infinite, infinitely strong. You wouldn't be spaghettified. That's too gentle a word. You'd be atomized, quantized, broken down past molecules, past atoms, past subatomic particles. Your very quarks would be torn apart. Whatever you were made of would cease to exist as structured matter. You'd become part of the singularity's incomprehensible state. Not dead, beyond dead, unmade. And here's the truly disturbing part. We don't know if information about you would survive. According to classical physics, everything that makes you you, your memories, your thoughts, your very identity would be lost, destroyed beyond recovery, erased from reality. But quantum mechanics insists information can't be destroyed, which means it has to go somewhere. But where? Into Hawking radiation billions of years later? Into another universe through a tunnel in space-time? Encoded somehow on the event horizon? We don't know. And that uncertainty might be the most horrifying aspect of the black hole's center. You wouldn't just die. You might be erased so completely that the universe itself forgets you ever existed. Or you might persist in some form we can't comprehend, locked in an information state that's neither existence nor non-existence. Quantum entangled with the black hole for eternity. Both possibilities are nightmarish in different ways. But at least we're speaking theoretically here, hypothetically. Black holes are rare, right? And we're nowhere near one. Wrong. There's one right at the center of our galaxy. We've photographed its event horizon. We've watched stars orbit it. And it's a monster. Let me introduce you to Sagittarius A, and let me tell you why it should terrify you. Chapter 6. Sagittarius. There's a monster at the heart of our galaxy, and we've been watching it eat. Its name is Sagittarius A, and it's a supermassive black hole sitting 26,000 light-years from Earth, right at the center of the Milky Way. It has a mass of 4 million suns, and it's been sitting there, lurking, for billions of years. We can't see it directly, but we've seen its effects, and they're terrifying. In the 1990s, astronomers at the Keck Observatory began tracking stars near the galactic center. They watched these stars orbit something invisible, something massive. The stars moved at incredible speeds up to 5,000 kilometers per second. That's nearly the speed of light. Something was holding these stars in orbit. Something with the gravitational pull of millions of suns, compressed into a space smaller than our solar system. They tracked one star in particular, S2. They watched it complete a full orbit around Sagittarius A in just 16 years. For a star to orbit that quickly, that close to an object means the object at the center must be incredibly dense. So dense that only one thing could explain it: a supermassive black hole. But the real confirmation came in 2019, when the Event Horizon Telescope captured the first image of a black hole's shadow. Not Sagittarius A at first, but its cousin in the galaxy M87. Then in 2022, they released the image of Sagittarius A itself. There it was, the heart of our galaxy, a ring of light surrounding a perfectly circular shadow, the event horizon, the point of no return. We were staring at the monster that's been watching over us for our entire existence as a species. But here's what makes Sagittarius A particularly disturbing. It's relatively quiet right now. It's not actively feeding. It's dormant, sleeping. But it wasn't always this way. Evidence from X-ray observations and radio emissions suggests that just a few hundred years ago, basically yesterday, in cosmic terms, Sagittarius A had a feeding event, Something fell into it, a cloud of gas, maybe a star that wandered too close. And when it fed, it lit up the galactic center like a beacon. Jets of radiation and particles shot out from near the event horizon. X-rays flooded the region. The monster was awake and feeding. Then it went quiet again. This is what supermassive black holes do. They lurk, they wait, and occasionally something wanders too close and they devour it. Then they go back to waiting. But here's what keeps astronomers up at night. We're watching stars get close. Really close. S2, the star I mentioned, has a closest approach to Sagittarius A of just 17 light hours. That's about 120 times the distance from Earth to the Sun, which sounds like a lot until you realize that Sagittarius A's gravitational influence extends much, much farther. And S2 isn't alone. There are dozens of stars in close orbits around the black hole. We've watched some of them for decades. We know their paths. And eventually, maybe not in our lifetimes, maybe not for thousands of years, but eventually one of them will get too close. We're going to watch a star die, torn apart by tidal forces, stretched into a stream of plasma spiraling into the event horizon. It's called a tidal disruption event, and it's one of the most violent phenomena in the universe. The star won't just explode or burn out, it'll be ripped apart, shredded, its atoms separated and superheated as they fall into the black hole, creating an accretion disk that glows brighter than billions of stars. And when that happens, when Sagittarius A feeds again, it's going to get very bright. The galactic center will light up. High-energy radiation will flood the region. Now, we're safe. 26,000 light-years is a very safe distance. The radiation won't reach us, and even if it did, our atmosphere would protect us. But it's still disturbing to know that at the heart of our galaxy, there's a cosmic predator waiting to feed. And there's something else about Sagittarius A that's deeply unsettling. It's surrounded by stars that shouldn't exist. Near the event horizon, conditions should be too violent for star formation. The tidal forces, the radiation, the sheer chaos of the environment should prevent gas clouds from collapsing into stars. And yet, there are young stars orbiting very close to Sagittarius A. Massive stars. Hot blue stars that are only a few million years old. How did they form there? How did they survive? We don't fully understand. Some theories suggest they formed farther away and migrated inward. Others suggest the black hole's gravity somehow facilitated their formation. But the fact that stars can form and survive in such a hostile environment is disturbing. It suggests that even close to a supermassive black hole, nature finds a way. Life, or at least stellar life, persists even in the shadow of the ultimate cosmic predator. Which raises an uncomfortable question. Could planets exist there? Could life exist on those planets? Imagine being an intelligent species that evolved on a planet orbiting a star near the galactic center. Every night, you'd look up and see the sky crowded with stars. Millions of them. Far more than we can see from Earth. The night sky would be brilliant with light. But you'd also see the effects of Sagittarius A, X-ray flares, relativistic jets, the occasional star being ripped apart. Your sky would be violent and chaotic. And if you developed astronomy, if you mapped the motions of the stars around you, you'd eventually realize the horrifying truth. Your sun is orbiting a black hole. Your entire world is caught in the gravitational well of a monster that could devour you at any moment. How would that affect your culture, your philosophy, your religion? Would you live in constant fear? Or would you accept the black hole as a god, a cosmic force to be worshipped and appeased? We'll never know. If such civilizations exist, they're 26,000 light-years away. any signals they send out would take 26,000 years to reach us. And they might not survive that long, because Sagittarius A is patient, but it's also hungry. And here's the truly terrifying thing about Sagittarius A. It's small. In the grand scheme of supermassive black holes, it's a baby. There are black holes out there that make Sagittarius A look like a speck of dust. Black holes with masses of billions of suns. Black holes that could swallow our entire solar system and not even notice. Black holes so massive that their event horizons are larger than the orbits of planets, where the tidal forces are so immense they could tear apart not just stars, but entire solar systems from light years away. But before we get to those monsters, we need to talk about the objects that are created when supermassive black holes feed. Because when a black hole eats, it doesn't just swallow matter quietly, it creates something that can be seen across the entire universe. It creates a quasar. And quasars are some of the most violent, most energetic, most absolutely terrifying objects in existence. Chapter 7. Quasars. In the 1960s, astronomers discovered something that shouldn't exist. Objects that looked like stars, but were brighter than entire galaxies. Objects that were so distant they had to be billions of light years away, yet so bright we could see them clearly with our telescopes. They called them quasi-stellar radio sources, quasars for short. And when scientists finally figured out what they were, the answer was more terrifying than anyone imagined. A quasar is a supermassive black hole in the process of feeding, actively devouring matter on a scale that's almost impossible to comprehend. And when a black hole feeds on that scale, it becomes the most luminous object in the universe. Let me put this in perspective. A typical quasar is brighter than 1 trillion suns. Some are brighter than 100 trillion suns. They outshine the entire galaxy they're sitting in the middle of. If you looked at a galaxy with an active quasar at its center, you wouldn't see the galaxy. You'd just see a point of blindingly bright light with a faint smudge around it. That's not the galaxy being dim. That's the quasar being so obscenely bright that it drowns out billions of stars. Now you might be thinking, okay, it's bright. So what? The sun is bright too. But you don't understand the scale. A quasar radiates more energy in 1 second than our sun will produce in its entire 10 billion year lifetime. 1 second of quasar output equals the entire energy budget of our star from birth to death. And quasars can stay active for millions of years. So where is all this energy coming from? From matter falling into the black hole. But not just any matter. We're talking about the mass of several suns per year being consumed. Entire star systems worth of material spiraling into the event horizon every single year. As this matter falls, it forms an accretion disk, a swirling vortex of plasma moving at significant fractions of the speed of light. The friction and magnetic fields in this disk heat it to temperatures of millions of degrees, hot enough to emit X-rays and gamma rays, hot enough to glow brighter than anything else in the universe. But the accretion disk isn't the scariest part. The scariest part is what happens at the poles. When a supermassive black hole feeds, it doesn't just glow, it shoots. Jets of matter and energy are accelerated to nearly the speed of light and blasted out from the poles of the black hole. These jets can extend for millions of light years, beams of destruction cutting through the cosmos like cosmic lightsabers. And if one of these jets points at you, you're done. The jets contain particles moving at 99.9 the speed of light. They're loaded with high-energy radiation, X-rays, gamma rays. If a quasar jet hit Earth, it would strip away our atmosphere in seconds. The radiation would sterilize the surface. Every living thing would die. Not from heat, not from impact, from raw, high-energy radiation tearing apart the molecular bonds that make life possible. And here's the truly horrifying part. We wouldn't see it coming. The jet travels at nearly the speed of light, which means it would arrive at almost the same time as the light telling us it exists. By the time we saw the quasar turn on and point at us, we'd have minutes at most before the jet arrived. Not enough time to do anything. Not enough time to evacuate or hide or prepare. We'd see our doom and die almost simultaneously. Now, fortunately, there are no nearby quasars pointing at us. The closest quasar is billions of light years away, and most quasars existed in the early universe when galaxies were younger and supermassive black holes were more actively feeding. But that doesn't mean we're safe, because every galaxy with a supermassive black hole at its center, which is most galaxies, has the potential to become a quasar. All it takes is enough matter falling in to trigger active accretion. And Sagittarius A, the black hole at the center of our galaxy, it was probably a quasar once, billions of years ago, when our galaxy was younger and more gas-rich. The Milky Way's core would have been a blazing beacon visible across the universe, which means there was a time when the center of our galaxy was uninhabitable, when the radiation flooding out from Sagittarius A would have sterilized any planet too close, when the Milky Way's heart was a zone of death. The fact that we exist means we either evolved after the quasar turned off, or we're far enough away that we were protected. But it's a reminder that our galaxy isn't always the safe, stable place we think it is. It has a violent past, and it could have a violent future, because quasars can turn back on. If Sagittarius A captured a large gas cloud, or if another galaxy merged with ours and funneled matter into the center, our black hole could reactivate. The galactic center could become a quasar again. It's unlikely to happen soon, but on cosmic timescales, it's almost inevitable. Eventually, the Milky Way will collide with Andromeda. The two galaxies will merge, and when they do, the chaos of the collision will funnel vast amounts of gas into both black holes. For a few million years, the merged galaxy will have two quasars at its heart, two supermassive black holes feeding simultaneously. The galaxy will become what astronomers call an active galactic nucleus, an AGN, and any planets near the galactic center will be bathed in lethal radiation. We'll be long gone by then. The collision won't happen for about 4 billion years. But it's a reminder that even our home galaxy isn't a permanent safe haven. It's just temporarily calm. But as terrifying as quasars are, they're at least predictable. They're the result of black holes feeding normally. Matter falls in, energy comes out. It's violent, but it's comprehensible. Our next destination is different because magnetars don't play by the normal rules. They're neutron stars on steroids, cosmic objects with magnetic fields so powerful they warp reality itself. And if you got too close to one, you wouldn't be torn apart by gravity or burned by radiation. You'd be erased by magnetism so intense it's almost magical. Chapter 8. Magnetars. Imagine a magnetic field so powerful it could kill you from 1,000 miles away, not by pulling metal objects toward it, not by inducing electrical currents, but by literally disrupting the atoms in your body. That's a magnetar. Magnetars are neutron stars with magnetic fields a quadrillion times stronger than Earth's. That's not a typo. Quadrillion. With a Q. We're talking about magnetic fields around 100 billion Tesla. To put that in perspective, the strongest magnetic field ever created on Earth was about 100 Tesla, and it lasted for a fraction of a second before the equipment exploded. A magnetar's field is 1 billion times stronger, and it's permanent. At those field strengths, magnetism stops behaving like the friendly force you play with using refrigerator magnets. It becomes something alien, something that bends reality. Let's start with the basics. A magnetar is what's left when a massive star goes supernova. The core collapses into a neutron star, a ball of neutrons packed so densely that a teaspoon of it would weigh 1 billion tons. The entire mass of a sun compressed into a sphere about 20 kilometers across. Now, all neutron stars have strong magnetic fields, but magnetars are different. During their formation, something goes wrong or right, depending on your perspective. The magnetic field gets amplified, twisted, concentrated. The result is an object with a magnetic field so intense it strains the very fabric of space-time. And that's not hyperbole. The magnetic field of a magnetar is so powerful it actually affects the quantum vacuum. Empty space isn't truly empty, it's filled with virtual particles popping in and out of existence. The magnetar's field is strong enough to polarize these virtual particles, making empty space birefringent. Light passing through it splits and refracts like light through a crystal. Space itself becomes optically active. But the real horror of magnetars isn't what they do to space, it's what they do to matter. Atoms are held together by electromagnetic forces. The electrons orbiting an atom's nucleus are kept in place by the balance between electromagnetic attraction and quantum mechanical repulsion. It's a delicate balance. Change the electromagnetic environment too much, and atoms can't exist. Within 1,000 kilometers of a magnetar, that balance breaks. The magnetic field is so strong, it warps the electron clouds around atoms. Atoms become elongated, stretched. Their chemistry changes. The molecules that make up your body would simply stop working. You wouldn't burn. You wouldn't freeze. Your atoms would just stop being able to be you. Your hemoglobin would stop carrying oxygen. Your proteins would denature. Not from heat, but from pure magnetic distortion of their molecular structure. Your neurons would stop firing because the chemistry they rely on would cease to function. You'd still be physically there, still technically alive for a few seconds, but your body would be chemically dead, and there would be nothing you could do about it. No shielding would help. The magnetic field would pass through any material like it wasn't there. But it gets worse, because magnetars aren't stable, they're violent. The magnetic field is so strong it strains the neutron star's crust. The crust is made of crystallized iron and other heavy elements, and it's much stronger than any material on Earth. But even it can't withstand the magnetic stress indefinitely. Every few years or decades, the crust cracks, a starquake. The surface of the neutron star shifts by a few millimeters. That doesn't sound like much, but remember, the crust is rotating hundreds of times per second, and it's held under the tension of an impossibly strong magnetic field. When it cracks, the magnetic field lines snap and reconnect, and that releases energy, an unimaginable amount of energy. These are called magnetar flares, and they're some of the most powerful explosions in the universe. In 2004, astronomers detected a magnetar flare from SGR 1806-20, a magnetar about 50,000 light-years from Earth. For a tenth of a second, this magnetar released more energy than our Sun produces in 150,000 years. The gamma-ray burst was so intense, it affected Earth's ionosphere from 50,000 light-years away. If that magnetar had been 10 light-years away instead of 50,000, the radiation would have caused a mass extinction on Earth. Our ozone layer would have been stripped away. The surface would have been bathed in lethal gamma rays. From 10 light-years away, that's farther than the nearest star to our Sun. Magnetars can kill across interstellar distances. And here's what really disturbs astronomers. We don't know how many magnetars there are. We've only discovered about 30, but that's because magnetars are only detectable when they're actively flaring. A dormant magnetar would be almost impossible to find, There could be thousands of them scattered throughout the galaxy, lurking, waiting for their next starquake, their next flare, and we'd never know they were there until they erupted. You could be looking at a seemingly empty patch of sky, not knowing that 10,000 light-years away, there's a magnetar preparing to flare. And when it does, the gamma rays will race towards you at the speed of light, arriving 10,000 years later with no warning. That's the insidious horror of magnetars. They're threats that travel at light speed. By the time you know they're dangerous, it's too late to run. But there's one more aspect of magnetars that's deeply disturbing, and it has to do with what they might become. Magnetars spin. All neutron stars spin, that's why we call some of them pulsars. They're like cosmic lighthouses, beaming radiation as they rotate. Magnetars spin too, though usually slower than regular pulsars. About once per 10 seconds typically, but they're slowing down. The intense magnetic field creates drag, a sort of magnetic braking. Over time, millions of years, magnetars slow down and their magnetic fields decay. Eventually they become dormant, just inert neutron stars. Dead, quiet. But what if the process could reverse? What if something could spin a dormant magnetar back up, re-energize its magnetic field? If two neutron stars collided and one of them was a dormant magnetar, the collision could restart it. Spin it up, reactivate the magnetic field. You'd get a zombie magnetar, a dead object brought back to terrifying life. And the collision would create a blast of gravitational waves and gamma rays that would be detectable across the entire universe. It would be one of the most violent events possible. In 2017, we detected the collision of two neutron stars, the first multi-messenger astronomy event combining gravitational waves and electromagnetic radiation. It was spectacular, beautiful, scientific gold. But imagine if one of those neutron stars had been a magnetar, the explosion would have been orders of magnitude more powerful. And if it happened close enough to Earth, say, within a few thousand light years, it could trigger a mass extinction. This isn't science fiction. Neutron star collisions happen, magnetars exist, the two will eventually combine. It's only a matter of time and distance. And that's the existential dread magnetars inspire. They're not just dangerous, they're unpredictably dangerous. They could be anywhere, could flare at any time, could be reactivated by events we can't foresee. We're living in a galaxy with invisible bombs scattered throughout it, any one of which could detonate without warning. But at least magnetars are local, galactic. They can't hurt us from other galaxies. They're a threat, but a bounded threat. Our next destination isn't bounded, because we're about to talk about a phenomenon that affects entire galaxy clusters. A cosmic current flowing across hundreds of millions of light years. A force that shouldn't exist, moving everything in its path towards something we can't see. Something beyond even the Great Attractor. They call it dark flow. And it might be evidence that there's something outside our universe, something massive, something pulling. Chapter 9. Dark Flow. In 2008, a team of astronomers dropped a bombshell on the cosmological community. They'd been studying the motions of galaxy clusters across a huge region of space, and they'd found something that shouldn't exist. A flow, a current. Hundreds of galaxy clusters spread across billions of light years, all moving in the same direction, all being pulled toward the same point. They called it dark flow, and it violates everything we think we know about the universe. Here's why it's so disturbing. According to our standard model of cosmology, the universe should be homogeneous and isotropic on large scales. That's fancy language for basically the same in all directions. There should be no special direction in space, no cosmic north or south, no preferred flow. Sure, Local structures like galaxies and galaxy clusters have their own motions. That's expected. But on very large scales, hundreds of millions of light years, all those local motions should average out. There should be no net flow in any particular direction. Dark flow violates this. Galaxy clusters separated by enormous distances, with no apparent connection to each other, are all moving in the same direction at speeds of up to 600 kilometers per second. That's over 1,000,000 miles per hour. Something is pulling them. Something massive. Something far away. And here's the truly terrifying implication. It might be outside our observable universe. Let me explain. The observable universe is limited. We can only see light that's had time to reach us since the Big Bang about 13.8 billion light years in any direction. That creates a boundary, a cosmic horizon. We literally cannot see beyond it because light from farther away hasn't had time to reach us yet. But just because we can't see beyond that horizon doesn't mean nothing exists there. The universe probably does extend far beyond what we can observe. And if there are structures out there, massive structures, they could gravitationally influence our observable universe. That's what some cosmologists think dark flow is. Evidence of a gravitational pull from something beyond our cosmic horizon. Something we can never see, can never observe directly, but that's affecting us nonetheless. Think about how unsettling that is. There could be structures in the universe so massive that their gravity reaches across the observable cosmos. Structures that dwarf superclusters, maybe superclusters, maybe something even larger, something we don't have a name for yet, and we're being pulled toward it, have been for billions of years, will continue to be for billions more. One proposed explanation is even more mind-bending. What if dark flow is evidence of another universe? In inflationary multiverse theory, our universe is just one bubble in an infinite foam of universes. These universes are usually causally disconnected, they can't affect each other. But if two universe bubbles are close enough, their gravitational influence might leak across the boundary. Dark flow could be the gravitational pull of another universe tugging on ours. An entire other reality, with its own galaxies, its own stars, its own physics, pulling on our cosmos from outside. If that's true, then dark flow is evidence that we're not alone. Not in the sense of alien life, but in the sense that our entire universe isn't alone. That reality is bigger than we imagined, stranger than we imagined. But not everyone accepts dark flow is real. It's controversial. Some follow-up studies have found supporting evidence. Others have failed to detect it. The effect might be an artifact of how we measure cosmic motion. Or it might be real, but weaker than originally thought. The controversy stems from how difficult these measurements are. We're trying to detect the motion of galaxy clusters hundreds of millions of light years away. We're looking for tiny shifts in the cosmic microwave background radiation as it passes through these clusters. The signals are subtle. The uncertainties are large. But if dark flow is real, it has profound implications. It would mean the universe isn't isotropic. There's a preferred direction, a cosmic axis, and that violates one of the foundational assumptions of modern cosmology. It would also mean there are structures or forces affecting us from beyond our observable universe. We're not isolated. We're connected to something bigger, something we can never fully observe or understand. That's a special kind of cosmic horror, the horror of the unknown unknown. Not just things we don't know, but things we can never know. Influences from beyond the edge of reality itself. And there's one more disturbing possibility. What if dark flow isn't constant? What if the pull is getting stronger? If it's caused by a massive structure beyond our horizon and we're falling toward it, then every year we get closer. Every year, the gravitational pull increases. Eventually, billions of years from now, we might cross some threshold. We might reach the structure-causing dark flow. What happens then? Do we merge with it? Does it consume us? Does our observable universe collide with whatever's out there? We don't know. We can't know, because it's beyond our horizon. By the time we get there, if we ever do, the universe will be so old, so different, that humanity, Earth, probably even the sun will be long gone. But here's the existential dread dark flow inspires. We're not in control of our cosmic destiny. Not just our galaxy, but our entire observable universe is caught in a current we don't understand, flowing towards something we can't see for reasons we may never fully comprehend. We're passengers on a cosmic ship we can't steer, and we don't know where we're going. But at least dark flow is pulling us somewhere. At least there's a destination, however mysterious. Our next terror is different, because rogue black holes don't stay in one place. They wander. They drift through the galaxy like cosmic predators, silent, invisible, deadly, and one could be heading toward us right now, and we'd never know until it was too late. Chapter 10: Rogue Black Holes. There's something moving through the Milky Way right now. Something massive, something invisible, something that could destroy our solar system without warning. It's a rogue black hole, and there might be hundreds of millions of them wandering through our galaxy. Let me explain how these cosmic nightmares are created. When massive stars die, they sometimes collapse into black holes. These stellar mass black holes typically have masses between 5 and 100 times that of our Sun. They're born in supernova explosions, violent deaths that light up the sky. But here's the thing: supernova explosions aren't always symmetrical. If the explosion is lopsided, it can give the black hole a kick. A gravitational recoil that launches it like a cannonball, sending it flying through space at speeds of hundreds of kilometers per second. The black hole becomes unmoored from its birthplace. It becomes a wanderer, a rogue. And once a black hole is moving, nothing stops it. There's no friction in space, no drag. It just keeps moving, forever, in whatever direction the supernova kick sent it, drifting through the galaxy like a shark through dark water. Now, you might think we detect these rogue black holes. After all, we have telescopes. We can see faint stars billions of light years away. Surely we'd notice a black hole wandering through our galactic neighborhood. But black holes don't emit light. They don't shine. The only way to detect them is if they interact with something, if they pass in front of a star and gravitationally lens its light, or if they accrete matter and produce X-rays. Most rogue black holes are just floating through empty space, not accreting, not interacting, completely invisible. They're out there. We know they must be. The physics is clear. But we can't see them unless we get very, very lucky. In 2022, astronomers got lucky. They detected a rogue black hole about 5,000 light-years from Earth by its gravitational lensing effect on a background star. The black hole passed directly between us and the star, and its gravity bent the star's light, briefly making it appear brighter and shifted. One rogue black hole, detected by pure chance, in our relatively small cosmic neighborhood. How many more are out there that we haven't detected? Statistical models suggest there could be 100 million stellar mass black holes in the Milky Way. Most are probably in orbit around normal stars, remnants of binary systems. But a significant fraction, maybe 10, maybe more, could be rogues, wanderers. 10 million invisible predators drifting through our galaxy. And here's what's truly terrifying. They don't care about us. They're not hunting. They're not targeting Earth. They're just moving, following the trajectories set by supernova explosions millions or billions of years ago. But if one of them happens to pass through our solar system, we're done. The black hole wouldn't need to hit us directly. It wouldn't even need to get particularly close. Just passing within a few light years would be enough to gravitationally disrupt the Oort cloud, the shell of comets surrounding our solar system. Those comets would be flung inward, thousands of them, maybe millions. The inner solar system would be bombarded. Earth would be hit over and over. Each impact would be an extinction event. The dinosaurs were wiped out by a single asteroid. Imagine thousands of comet impacts over a few centuries. Nothing would survive. The oceans would boil. The atmosphere would be stripped away. The surface would be sterilized. And we'd see it coming. We'd watch the rogue black hole approach, watch it disturb the Oort cloud, watch the death heading toward us over decades or centuries, and be powerless to stop it. But a distant pass is the merciful scenario. If a rogue black hole passed within the orbit of Neptune, the entire outer solar system would be destabilized. Neptune, Uranus, Saturn, possibly even Jupiter could be ejected from the solar system or sent into wildly elliptical orbits. The gravitational chaos would reshape the solar system. Mars might collide with Earth. Earth might be flung into an orbit farther from the Sun, freezing the planet. Or closer, turning it into another Venus. The solar system we know, the stable orbital arrangement that's persisted for 4.5 billion years, would be destroyed in just a few thousand years of gravitational chaos. And if the rogue black hole passed even closer, if it came within the orbit of Mars, Earth would be ejected, flung out of the solar system into interstellar space. We'd become a rogue planet, freezing, darkening. The sun would become just another bright star in the sky, growing dimmer year by year as we drifted away. The oceans would freeze. The atmosphere would condense and fall as snow. Within a century, Earth would be a lifeless ice ball hurtling through the darkness. That's not hypothetical. That's what happens when a rogue black hole passes too close to a planetary system. And it's happening somewhere in the galaxy right now. Somewhere, a rogue black hole is destroying someone else's solar system. Or maybe it's already happened to us, and we're living in the before times, blissfully unaware that our doom is already in motion. Because here's the thing, we wouldn't see it until it was close. A rogue black hole moving at 200 kilometers per second would cross from beyond Pluto's orbit to Earth's orbit in less than 10 years. That sounds like a lot of warning, but consider, we'd first have to detect it, confirm it's a rogue black hole and not some other phenomenon, calculate its trajectory, realize it's heading toward us, and then, what? There's nothing we could do. No way to deflect a black hole, no way to evacuate Earth, no way to stop it. We just have to watch and wait. That's the psychological horror of rogue black holes. They represent a completely unstoppable, unpreventable apocalypse scenario. Not caused by our mistakes or our technology or our politics, just bad luck, being in the wrong place at the wrong time on a cosmic scale. And it gets worse. Because stellar mass rogue black holes aren't the only ones wandering the galaxy. There might be intermediate mass black holes too. Black holes with masses of thousands or even hundreds of thousands of suns. These would have formed from the collapse of massive star clusters or from mergers of smaller black holes. And if those got a supernova kick, they'd be wandering too. Invisible, massive, deadly. An intermediate mass rogue black hole passing through our galaxy wouldn't just destroy individual star systems, it would disrupt entire regions of the galaxy. It would fling thousands of stars into chaotic orbits. It would trigger waves of star formation and destruction as it passed. Have such events happened in the Milky Way's past? Almost certainly. The galaxy is 13 billion years old. There's been plenty of time for wandering black holes to wreak havoc. Are they happening now? We don't know. We can't see them unless they happen to interact with something we're already observing. The galaxy could be full of wandering monsters, and we'd be oblivious. But here's perhaps the most disturbing aspect of rogue black holes. Some of them might be binary systems. Two black holes orbiting each other, both wandering through the galaxy together. These binary black holes are slowly spiraling toward each other, losing energy through gravitational wave radiation. Eventually, maybe millions of years from now, maybe tomorrow they'll merge. And when two black holes merge, it's one of the most violent events in the universe. They release more energy in gravitational waves in the final second than all the stars in the observable universe are emitting as light. The fabric of space-time itself ripples like water, waves propagating outward at the speed of light. If a binary black hole merger happened within a few hundred light years of Earth, the gravitational waves could be intense enough to affect us. Not catastrophically, probably not, but measurably. Tidal forces on Earth might increase slightly. Seismic activity might be triggered. The exact effects are uncertain because we've never observed such a close merger. And we wouldn't know it was coming. Binary black holes are invisible until they merge. The merger itself generates a burst of gravitational waves that we can detect. That's how LIGO found them. But until that burst, they're just two invisible masses orbiting in the dark. We could have a binary black hole system nearby right now, days away from merging, and we'd have no idea until the gravitational waves hit us. That uncertainty, that inability to see the threat until it arrives, is what makes rogue black holes so terrifying. They're not hypothetical, they're real, they're out there, they're moving, and one day, one of them might wander too close to home. But as scary as stellar mass rogue black holes are, they're nothing compared to what's lurking in the deep cosmos. Because there are black holes out there so massive, so incomprehensibly huge, that they make Sagittarius A look like a grain of sand on a beach. Black holes that could swallow our entire solar system and barely notice. Let me introduce you to TON 618, the largest black hole ever discovered, and quite possibly the most terrifying object in the entire universe. Chapter 11. TON 618. There is a black hole so massive that if you put it where our Sun is, its event horizon would extend past the orbit of Neptune. The entire inner solar system would be inside it. Mercury, Venus, Earth, Mars, Jupiter, Saturn, Uranus, Neptune, all of them would be inside the point of no return. Its name is TON 618, and it has a mass of 66 billion suns. Let me say that again. 66 billion suns. Not million. Billion. It's so massive that it defies comprehension. So massive that scientists aren't entirely sure how it got that way. So massive that its very existence challenges our theories of black hole formation and growth. TON 618 is a hypermassive black hole. The term supermassive isn't enough. It's in a category beyond that. And it sits at the center of a galaxy 18 billion light-years away from us. When we look at TON 618, we're seeing it as it was 18 billion years ago, which is impossible, by the way, because the universe is only 13.8 billion years old. How are we seeing something from 18 billion years ago? The answer is cosmic expansion. That galaxy was much closer when it emitted the light we're now seeing, but space has been expanding, carrying the galaxy away from us. By now, that galaxy is much, much farther away than 18 billion light-years. But that's not the disturbing part. The disturbing part is what TON 618 is doing. It's feeding. Actively, voraciously. It's an ultraluminous quasar, pouring out energy at a rate that's almost incomprehensible. TON 618 is generating the energy of 140 trillion suns, not over its lifetime, right now, continuously. To power that output, it's consuming the equivalent of one Earth mass every minute. Every 60 seconds, a planet's worth of matter crosses its event horizon and is annihilated. Actually, that's not quite right. It's consuming far more than that. Most of the matter falling toward TON 618 doesn't cross the event horizon. It spirals in the accretion disk, gets superheated, radiates energy, and then eventually falls in. Only a small fraction of the infalling matter's energy is radiated away. The rest crosses the event horizon. So TON 618 is actually consuming the equivalent of several planets per minute. Maybe more. We can only measure what we see radiating. The black hole itself is hidden behind the blazing accretion disk. Now let's talk about the scale of this monster. The event horizon of TON 618 has a diameter of about 1,300 astronomical units. 1 AU is the distance from Earth to the Sun, so the event horizon is 1,300 times that distance across. To put that in perspective, the orbit of Pluto is about 40 AU from the Sun. The event horizon of TON 618 could contain 32 complete solar systems the size of ours, arranged in a line. Or think of it this way. If you were at the center of TON 618 and could somehow survive, and you looked around, the event horizon would be farther away than Neptune is from us. You'd be standing at the center of a space larger than our solar system, and all of it would be inside the point of no return. Light trying to escape from near the event horizon would be so redshifted, so stretched by the gravitational field, that it would become invisible. The event horizon wouldn't look like a surface. It would look like a gradual darkening of space in all directions, like being inside a sphere of shadow that extends farther than you can see. And if you were falling toward TON 618, the experience would be surreal. Remember I mentioned that with supermassive black holes, you can cross the event horizon intact? TON 618 takes that to an extreme. The tidal forces at the event horizon are so weak relative to the black hole's size that you could cross it without even noticing. You'd be falling, accelerating. But the event horizon is so far from the center that the gravitational gradient is gentle. You wouldn't be spaghettified, you'd be fine, physically intact. And that's what makes it psychologically horrifying. You'd cross the point of no return without realizing it. You'd be doomed, and you wouldn't know. You might figure it out eventually. You might notice that no matter which direction you pointed your engines, you were still falling toward the center. You might realize that the stars behind you were becoming unreachable, their light unable to follow you past the event horizon. But by then, it would be hours too late, maybe days. You'd have time to think about your fate, time to contemplate that you were now in a region of space cut off from the rest of the universe, time to realize that you had hours or days left before the tidal forces near the singularity finally tore you apart. That slow realization of doom might be worse than instant death. But here's what really disturbs astrophysicists about TON 618. It's too big. Black holes grow by accreting matter. They pull in gas and dust and stars, and they get bigger. But there's a limit to how fast they can grow. It's called the Eddington limit. When a black hole accretes matter, the infalling matter heats up and radiates. That radiation pushes back on the infalling matter. If the black hole tries to eat too fast, the radiation pressure blows the food away. It's self-limiting. Given the Eddington limit, we can calculate how big a black hole could grow over the age of the universe. And TON 618 is bigger than that, much bigger. It's like finding a tree that's 200 feet tall, but the tree is only 10 years old. Trees don't grow that fast. Something's wrong. So how did TON 618 get so massive? One theory is that it formed from a direct collapse of a massive gas cloud in the early universe. Instead of forming a star first and then having that star collapse into a black hole, the cloud just collapsed directly into a massive black hole. A shortcut. These are called direct collapse black holes, and they could have formed with initial masses of thousands or even millions of solar masses. Then they could have grown through accretion, reaching the sizes we see today. But even that might not be enough to explain TON 618. It's just so damn big. Another theory is that TON 618 grew through mergers. When galaxies collide, their central black holes eventually merge. If TON 618's galaxy underwent multiple mergers in its early history, the black hole could have grown quickly by cannibalizing other black holes. But that raises another disturbing question. If TON 618 grew through mergers, and it's 66 billion solar masses now, how big were the black holes it merged with? They'd have to be enormous themselves, billions of solar masses each. Where are those black holes? Are there others out there as big as TON 618? Bigger? We don't know. TON 618 is the largest we've found, but we've only surveyed a tiny fraction of the universe. There could be even more massive black holes lurking out there, waiting to be discovered. And here's a thought that keeps cosmologists awake at night. What's the upper limit? Is there a maximum size a black hole can reach? Or could they grow indefinitely, eventually consuming entire galaxy clusters, becoming incomprehensibly massive? In the far future of the universe, trillions of years from now, as galaxies merge and black holes coalesce, we might end up with black holes even larger than TON 618. Black holes with masses of trillions of suns. Black holes whose event horizons are measured in light years. Black holes that are, for all intents and purposes, small universes unto themselves. And that brings us to a disturbing philosophical question. Could we be living inside a black hole right now? Think about it. Inside a black hole's event horizon, all paths lead to the singularity. You're forced to move forward in space toward the center. That's disturbingly similar to our experience with time. We're forced to move forward into the future. We can't stop. We can't go back. Some physicists have speculated that our universe might be the interior of a black hole in some larger parent universe. That the Big Bang was actually the formation of a black hole as seen from the inside. That the singularity we're all heading toward isn't in the past, it's in the future. The Big Crunch. The end of everything. If that's true, then we're all already past the point of no return. We're all falling toward a singularity trillions of years in our future. And there's nothing we can do to escape. That's not mainstream cosmology. Most scientists don't believe we're inside a black hole. But the math allows for it. And that's disturbing in itself, that our best theories of reality allow for us to be trapped in a cosmic prison without even knowing it. But let's return to TON 618, because there's one more aspect of this monster that's genuinely terrifying. It's young. TON 618 existed when the universe was less than 1 billion years old. It's one of the earliest quasars we've ever detected, which means it's been feeding for a very long time. But quasars don't last forever. Eventually they run out of fuel. The accretion disk empties. The jets shut down. The quasar goes quiet and becomes just a dormant supermassive black hole. TON 618 probably isn't a quasar anymore. Remember, we're seeing it as it was 18 billion years ago, accounting for the light travel time and cosmic expansion. The TON 618 that exists now, today, has evolved for billions of years since then. It might be dormant now, quietly lurking at the center of its galaxy, waiting for more matter to fall in. Or it might be even bigger. It might have continued feeding. It might have merged with other black holes. It might now be 100 billion solar masses, or more. We won't know for billions of years. The light showing us what TON 618 is doing right now won't reach us until long after humanity is gone. That's the cosmic horror of TON 618. It's not just massive, it's beyond our ability to comprehend or observe in real time. It's a monster so distant that we can only see its ancient past, never knowing what it's become in the eons since. But at least TON 618 is far away, incomprehensibly far. It can't hurt us. Our final destination is different, because we're going to talk about a place that might not be a place at all, a boundary that might not be a boundary, the edge of everything we can ever know or see or reach. We're going to the edge of the universe, and what we find there is far stranger than you imagine. Chapter 12. The Edge of the Universe. Let me ask you a question that sounds simple. Where is the edge of the universe? Most people would say, there is no edge. The universe is infinite. And maybe that's true. But even if the universe is infinite, there's still an edge. Not an edge to space itself, but an edge to what we can see. An edge to what's reachable. An edge to reality as we can experience it. They call it the cosmological horizon, or the particle horizon, or the observable universe limit, and it's about 46.5 billion light-years away in every direction. Wait, you might say, the universe is only 13.8 billion years old. How can we see things 46.5 billion light-years away? Hasn't light only had 13.8 billion years to travel? Good question. The answer is cosmic expansion. The light from distant galaxies has been travelling toward us for 13.8 billion years. But during that time, space itself has been expanding. So those galaxies are now much farther away than 13.8 billion light-years. In fact, the galaxies at the edge of our observable universe are now about 46.5 billion light-years away. And they're receding from us faster than the speed of light. Wait, nothing can move faster than light? True, nothing can move through space faster than light, but space itself can expand faster than light. And in fact, at sufficient distances, space is expanding so fast that light from those regions will never reach us. Ever. Those galaxies are beyond what we call the cosmological event horizon. They're not just far away, they're unreachable, forever. No matter how long we wait, no matter what technology we develop, we will never be able to see them or visit them or communicate with them. They might as well not exist as far as we're concerned. They're causally disconnected from us, outside our reality. And here's the existential horror. Every day, more galaxies cross that horizon. Every day, the universe we can see gets smaller. Right now, thousands of galaxies are slipping away, accelerating beyond the cosmological event horizon. Their light, which has been travelling toward us for billions of years, will stop making progress. The space between us and them is expanding faster than the light can traverse it. They're being erased from our universe, not destroyed, not dying, just becoming unreachable, fading into a realm beyond our cosmic horizon, leaving us behind. And there's nothing we can do to stop it. This is the long-term fate of our universe. In the far future, trillions of years from now, the accelerating expansion of space will have carried away almost all galaxies beyond our horizon. Future civilizations will look up at the night sky and see nothing, just the stars in their own galaxy, and maybe a few galaxies in their local cluster that are gravitationally bound together. Everything else will be gone, fallen over the edge of the universe. Those future civilizations will develop cosmology, will study the universe, and will conclude that they're alone, that their galaxy cluster is the entire universe. They'll have no evidence that billions of other galaxies ever existed. The universe will have forgotten its own history. But it gets worse, because eventually, even stars in our own galaxy will be unreachable. As space continues to expand, accelerating due to dark energy, the distances between stars will grow, not noticeably at first. But over trillions of years, stars that are gravitationally unbound will drift apart. Eventually, each star will be alone in an expanding bubble of space. Trillions of years from now, if a planet orbited one of those stars and somehow supported life, the inhabitants would look up at the night sky and see nothing, not even other stars, just darkness. They would be completely, utterly alone in an empty universe. And they would have no way to know that the universe was once full of galaxies and stars and light. No evidence, no fossils, nothing. Their universe would be just their star and the darkness. That's the eventual fate of everything. Heat death, cosmic loneliness. The expansion of space eventually isolating every structure until nothing can interact with anything else. But let's return to our edge, to the cosmological horizon we face today, because there's something deeply strange about it. When we look at the edge of the observable universe, we're looking back in time. We're seeing galaxies as they were 13.8 billion years ago, shortly after the Big Bang. We're seeing the cosmic microwave background, the afterglow of the Big Bang itself. But what's beyond that? What's beyond the edge? We don't know. We can't know. We'll never know. It's not just that we lack the technology to see that far, it's that the light from beyond the edge hasn't had time to reach us yet. And because space is expanding, it never will. There could be anything beyond that horizon. More galaxies like ours. Galaxies with different physics. Other universes. Cosmic structures we can't imagine. Or nothing at all. We have no way to find out. That uncertainty, that fundamental inability to know what's beyond our horizon is unsettling. We're trapped in a bubble of observable space, unable to see beyond it, unable to reach beyond it, unable to know what's really out there. It's like being in a room with walls you can't touch or see, knowing there's something beyond but having no way to discover what it is. And that brings us to one of the most disturbing questions in cosmology. Is the universe we see typical of the universe as a whole? Maybe we're in a special region, a bubble of normal physics in a sea of chaos. Maybe the laws of physics we observe, the speed of light, the strength of gravity, the charge of electrons, are just local rules. Maybe beyond our horizon, those laws are different. Maybe the universe beyond our edge is so alien that matter as we know it can't exist there. Maybe it's full of exotic structures we can't even conceive of. Or maybe, and this is perhaps most disturbing, we're in a false vacuum. The quantum fields that define our universe might be in a metastable state. Not the lowest energy state possible, but a local minimum. Like a ball balanced in a bowl on a hillside. Stable for now, but not truly stable. If that's true, then somewhere in the universe the vacuum could decay. A bubble of true vacuum, a region where the quantum fields have fallen to a lower energy state, could form. And that bubble would expand at the speed of light, converting our universe into something else. Something where the laws of physics are different. Inside the bubble, chemistry wouldn't work. Atoms would dissolve. Stars would go out. Everything would unravel, and we'd never see it coming. The bubble of destruction would travel at light speed. We'd die the instant it reached us with no warning. The edge of the universe would suddenly become lethal, rushing toward us at 300,000 kilometers per second. Is this happening? Is there a bubble of vacuum decay expanding through the universe right now? We don't know. The math says it's possible, maybe even likely, given enough time and space. But here's the terrifying implication. If vacuum decay is happening anywhere in the infinite universe, it's probably happening in multiple places. Multiple bubbles of true vacuum, each expanding at light speed, converting the universe as they go. Eventually, these bubbles will collide, and when they do, the collision will release enormous energy. The boundary where two different vacuum states meet could be a region of intense radiation and exotic physics. The universe beyond our horizon might not be empty. It might be a battlefield of colliding vacuum bubbles, each rewriting the laws of physics as they expand. And we're just sitting here, in our little bubble of false vacuum, waiting for the day when one of those bubbles reaches us and erases everything we know. That's the ultimate cosmic horror. Not monsters coming to get us, not black holes swallowing us, but the possibility that reality itself is temporary, that the laws of physics we rely on could change at any moment, and there would be nothing we could do to stop it or survive it. But even if vacuum decay doesn't happen, we're still facing the edge, still confronting the limits of what we can know. And there's something philosophical terrifying about that. We're creatures who want to understand, who need to explore, who can't stand not knowing. And the universe has given us an absolute fundamental limit to what we can ever know. There are things beyond our horizon that we will never see, questions we will never be able to answer, truths we will never discover. No matter how smart we get, no matter what technology we develop, no matter how long we survive as a species or how far we evolve beyond our current form, there will always be an edge we cannot cross, a horizon we cannot see beyond. We are permanently, fundamentally, cosmically limited. And maybe that's the most terrifying thing of all. Not physical danger, not death, but the knowledge that reality is bigger than we can ever comprehend, that most of the universe is beyond our reach, that we're trapped in a tiny bubble of causally connected space, and everything else might as well not exist. We're alone. Not because there's no one else out there, there probably is, but because the universe is so vast and expanding so fast that we'll never meet them. We'll never know they exist. We'll just drift apart in the dark, each species alone in their own bubble, unable to ever connect. That's the true horror of the edge of the universe. Not what's there, but what we'll never know is there. 12 of the most terrifying places in the universe. Places that challenge our understanding of reality. Places that could kill us in ways we can barely comprehend. Places that might already be affecting us right now in ways we don't yet understand. The Great Nothing, showing us that the universe has holes we can't explain. The Eridanus supervoid, suggesting that reality itself might be different in different places. The Great Attractor, proving we're not in control of our cosmic destiny. Black hole event horizons, where the point of no return is invisible and inescapable. Black hole singularities, where physics itself breaks down. Sagittarius A, the monster at the heart of our galaxy. Quasars, turning black holes into cosmic flamethrowers. Magnetars, where magnetic fields become so intense they warp reality. Dark flow, suggesting there's something beyond our universe pulling on us. Rogue, black holes, wandering through the galaxy like invisible predators. Ton 618, a black hole so massive it defies our theories of how black holes can form, and the edge of the universe, reminding us that most of reality is forever beyond our reach. But here's the thing, as terrifying as all of these places are, they're also beautiful. They're evidence that the universe is stranger, more complex, more wondrous than we ever imagined. Every one of these phenomena tells us something about how reality works. They push the boundaries of physics, they challenge our assumptions, they force us to think harder, dig deeper, and ask better questions. And yes, they could kill us, but they probably won't. The universe is vast. The dangerous places are mostly far away. We're living in a relatively calm, safe corner of the cosmos, for now. But these places are out there. They're real. They're waiting. And the fact that we can know about them, can study them, can begin to understand them, that's the miracle. We're matter that became conscious, atoms that learned to think, star stuff contemplating the stars. And we've looked out into the darkness and mapped the monsters lurking there. That takes courage. That takes intelligence. That takes a species that refuses to look away just because something is scary. So yes, the universe is full of terrifying places, but we're still here, still looking, still learning, still asking, what's out there? And maybe that's the most important thing. Not that the universe is scary, but that we're brave enough to look at it anyway. Thanks for watching. If you enjoyed this journey to the scariest places in the universe, hit that like button and subscribe for more. Let me know in the comments which of these cosmic horrors scared you the most. And remember, the universe is vast, it's strange, it's terrifying, but it's also home.